Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. Do you realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world? Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. Justin, VK7 TW at the microphone, and hello to Paul out in there in streaming land. And if you are watching, I think we've got about 5 people watching tonight out in streaming land. Please let us know who you are and what where you're coming from, and if you've got any questions, please put them in the chat, and we'll endeavour to answer them. We've got a bit of a blast from the past to start off with, and a bit of absolutely what I find fascinating history. People are probably, I can hear the groans out there, but absolutely fascinating history of instrumentation and the development during the Victorian era and the Industrial Revolution and all of this sort of stuff. And so there's a bit of that and a bit of a demonstration. I didn't sacrifice the demonstration gods beforehand, and when I switched everything on, of course it didn't work, but it's just magically come right. So we have all systems go for a demonstration. Now, before we get underway, I'll just do an acknowledgement of country. I wish to acknowledge Tasmanian Aboriginal people as the traditional owners of the land upon which we're presenting tonight, and pay my respects to elders past, present and emerging, for they hold the memories, the knowledge, the culture and hopes of Aboriginal Tasmania. So, without further ado, I'll flick over to... We have a beautifully made box and an instrument. Now, this is what they call a Cambridge portable potentiometer, and I will go through what that actually means. I just grabbed the the wonderful instructions that came with this particular device. Oh, that was good, wasn't it? Let's try that. That's a bit better. So, now, these instructions are for a much older unit than this particular unit, but it is the same in the same series of units. This is instructions for the use and care of the Cambridge Portable Potentiometer workshop pattern, and I love this bit. This book is intended for the man who has charge of the apparatus. So at this stage, I haven't really got charge of the apparatus, but we'll we'll work on that one. But I just wanted to go through a little bit of history. Way back when electricity was being discovered, and they needed to measure it, they were doing all sorts of experimentation with it. In fact, this is in the era of radio. So started off with telephone. We had this wonderful thing called wireless, which was created by a whole range of people. One of them, probably the best known, is Marconi, and did a whole lot of experimentation with it. But you had to have test equipment to ensure that things were at the right voltage or the right current or the right resistance, or etc., etc. And so when people in the before wonderful digital multimeters and all of this sort of stuff had to measure very, very small voltages and had to measure them accurately, we had things like and hello to Lionel and Paul Pruss, a bit on Henry Sutton sometimes. Definitely Paul. Henry Sutton is one of Robin Williams' favourite top 100 scientists. So there you go. Now Robin Williams is, of course, our host of the Science Show, which is broadcast every Saturday. So I hope one day to be the man who has charge of the apparatus. Well, I have that wish as well, Lionel. I definitely have that wish as well. But so to measure very, very small voltages, you could use a range of devices. One of them was a potentiometer, and there was the creation in the early 19th. Late 19th century, I'll get that right, so 1890s, into the early 20th century, there was standard cells were created, electricity, chemistry, physics was exploding, and so some bright spark at Cambridge University came up with, and we're talking about the Rutherford Lab and the wonderful stuff that came out of Cambridge University, but I'm getting ahead of myself here. What came out of those experiments was the creation of the Cambridge Instrument Company. Now, we're talking, the Cambridge Instrument Company ran from 1881 to 1988, would you believe? So it was basically formed to make instruments, scientific instruments, primarily when it started for Cambridge University. Now, the fascinating thing about this company is it was started by Horace Darwin, 1851 to 1928. Now, that Horace Darwin was Charles Darwin's, so the father of evolution, or the grandfather of evolution, or whatever you want to call Charles Darwin. That was Darwin's ninth son, youngest son, and created this company to supply the laboratories at Cambridge University. The Darwin Family Association continued all the way through until the 1970s. So there was a Darwin involved with the company. It moved around. It was taken over by R.W. Pye Instrument Company in about 1919, and there's a bit about R.W. Pye shortly. And then 1968, it was merged off into the Brown Boveri and Company, so the BBC, and then later merged with the Swedish company AEA, and so it became ASEA Brown Boveri. Now, they're, if you're in the electrical trade, they're very well known as makers of switchgear and makers of electrical equipment. Beautifully made equipment. So all the way through to ABB now own this particular company that creates test equipment and switchgear and all sorts of stuff. But there's some interesting things. A lot of the ex-employees of the Cambridge Instrument Company went off to found other companies which may be familiar to people. There was many ex-employees founded, and one in particular was a William T. Pye, P-Y-E, who joined as a foreman in 1880 and left in 1898. He formed the W.G. Pye Instrument Company with his son, ultimately to branch out into the Pye Radio Ltd company. And Pye radios are very well known in Australia as valve equipment that was modified by amateurs. So there's a linkage to Pye radio in there as well. Now, R.W. Paul, this is another little fascinating linkage here. R.W. Paul, Robert William Paul, 1869 to 1943, who'd previously worked for Elliott Bros. Now, Elliott Bros, for those who are into computer history, Elliott Bros, Elliott Computer, they were one of the first companies to get into commercial computing, and they produced an Elliott. And in fact, I think if my memory serves me correctly, the University of Tasmania had an Elliott computer very early on in its in computing days in the computing department. Somebody can correct me there, but I think he worked for the Elliott Brothers, trained as a scientific instrument maker, and went on. He actually came up with the much more robust and easy to use single pivot moving coil, a very sensitive instrument, and in fact one that ended up in the potentiometers, the galvanometer meter, which I'll show you, as a very sensitive, very sensitive meter, which was used in these sort of instruments. The Unipivot, it ended up becoming the Unipivot galvanometer, proved to be very successful, and within a few years a large number of variants and accessories for a wide range of electrical instrument measurements were being made. And Robert Paul went on within the enlarged organisation for the rest of his life. He also became a cinematic pioneer in the 1890s, and there's a couple of links I'll put on the video description to his work, and we're talking about movies, so moving pictures in the 1890s, which is pretty spectacular if you think about it, moving picture history. And so one of the other employees, Eric Moullin, 1893 to 1963, was the Cambridge Professor of Electrical Engineering and also the President of the Institution of Electrical Engineers, or the IEE, which ended up becoming the IEEE. He invented the first vacuum tube voltmeter, which he described in a paper to the IEE in December of 1922. So this would have been at the absolute cutting edge of valves, at the beginning of valves taking over the world. Just absolutely phenomenal. So there's linkages into all sorts of things, and so this was produced. This is about a 1950s model. It is a 44228, which is a later model, and I've got I have a manual on its wending its way to me for the 44228 because it's slightly different to this one. But you'll see. Just to give you an idea of the sort of things that are inside the box, and I have to say it's not it's not really that spectacular inside the box. It's all pretty normal stuff. If we zoom in here a little bit, this is the circuit diagram for an earlier model of the potentiometer, but you'll notice there are a couple of 1.5 volt D cells in the 1950s version. these were 1.5 volt large batteries. You can see here each of these was 1.5 volts. They divided that 1.5 volts down, and they had a coarse and a fine potentiometer. So this was the voltage source, the potential source over here. The actual potentiometer side of it was over this side, and you'll see that there is a main switched potentiometer, and then there is a fine Rheostat type potentiometer. So fine dial. There is the other 1.5 volt. There is a little bit of a divider arrangement here, and then there is a switch sitting around the galvanometer, which enables you to go to the test. So the test, whatever's coming in through the test terminals, or you could switch to the standard cell. Now the Weston standard cell, I showed a Weston standard cell a couple of DATV nights ago. The Weston standard cell is a standard chemical reaction which enables and gives a steady voltage of 1.018 and a number of other decimal points based on the temperature, and it is an incredibly stable voltage source. And up until about 20 years ago, it was the standard voltage, the standard for voltage, up until they went to a different way of generating voltage, actually through an RF process. That's a whole ATV night in itself. But this contains a standard cell, and you could then compare the voltage coming in here to the divider that was on the standard cell, and enable a comparison to be made so that you could work out what was coming in here, because you had known knowns in the standard cell or the voltage arrangement that you had here. So you could compare between the test voltages and the standard, and so you could end up with a quite an accurate, and we're talking about an accuracy of like 5 or 6 digits, so 5 or 6 decimal points, and I'll show you how you do that in a sec. So and as it comes, so as it normally is, let me switch to, as it comes like this, you can measure up to 100 millivolts, so 0.1 of a volt. And you, as it currently stands, it's only a voltage device, but of course you could put some shunts in there, standard shunt resistors, and you could measure current, and the current could be dependent on the shunt all the way up to probably about 1,000 amps. You could put in resistive dividers, standard resistive dividers, which could take it up to, what do they say, up to 500 volts. So all those resistive dividers divided down to the 100 millivolt range, and then you could accurately measure those higher voltages to a high degree of accuracy. It is an incredibly sensitive device, and in fact, one of the things I will show you is the galvanometer has a clamp on it. Whenever you try and move it, you need to clamp the galvanometer so it doesn't go off on its merry way and damage itself. There is a standard cell inside the box. Now, in a future program, I'm hoping to be able to show you all of this inside the box. I haven't been able to get inside the box yet because there are a few problems with this particular device. I think one of the rheostats has a bit of an issue, and I'm not sure the standard cell is actually giving the standard voltage. So I'm going to need to do a little bit of investigation and see. I suspect the mercury's probably moved in the standard cell from one chamber to another. But anyway, now let me try and demonstrate. So what I've actually done here, I'll move this over and I'll move a microphone down here so people can hear me. So what I've got on this side, which I'll just turn it around a little bit, what I've got on this side is, apart from the multimeter, this is a bit of a special power supply. This enables me to create, let me see whether I can zoom in here a little bit. This enables me, this is actually a piece of ex-hydroelectric commission equipment that they threw out. This was would have been used in a test lab, in like a protection circuit test lab, and it enables you to generate 1 through 10 volts, but the key ones are 1 millivolt, 2.5 millivolts, 5 millivolts, 10 millivolts, 50 millivolts, 100 millivolts, 500 millivolts, 1 volt, 5 volt and 10 volts. But also it has a dial on here which enables you to, for each of these scales, put in a particular percentage. But the key thing here that I'm using it for is, I've got it set to, I think, about 5 millivolts, and I've got it turned all the way up to 100%. So what's coming out the back of this unit is 5 millivolts of voltage. So it enables me to give me a test voltage that I can then, with my potentiometer, measure what the actual voltage is to about 5 to 6 decimal points. So how do we do that? Now, I'll just point out the different parts of the potentiometer. This bit is the galvanometer. So this is a really sensitive device. It sits on a single strand. You can see here there's a little lever here which goes from one side to the other. I've got it in the free setting, so it's actually free to move as it wants for the really small currents that run through it. And when you move the device, the first thing you do is put it into clamp, and it clamps off the device so the meter movement doesn't move. Over here you've got your underneath the white bit here, you've got a voltage source. So this is a voltage source which is derived from there is a couple of D cells, 1.5 volt D cells in the box, in the side of the box, and this enables you to dial up to 100 millivolts, and then there's a fine potentiometer, and then this is the switch which enables you to switch between the 1 input or the 2 input. Oh, hang on, let me go a bit further over. The 1 input or the 2 input, and you'll notice here there is a mercury thermometer here which is giving me the temperature. Now the reason the mercury thermometer's there is the Weston standard cell that's inside the box, actually the accuracy of the cell, you need to know, has a calibration curve on it which comes with the cell. And you need to know what the temperature is to enable you to give you the 4th, 5th and 6th digits of the voltage. So it gives you, out of the box, it gives you 1.018 volts, and then the rest of that, the couple of digits, is determined by the temperature, and that's why you have a mercury thermometer sitting there. Now, the other two, the two. Now, let me see how we do this. Let me go down a bit here without it falling over. You've got switched potentiometer here. So it's got a little indentations on it. So this gives you a millivolt each. So this is 0 to 100 millivolts. And it gives you the ability to set that. So this is your coarse setting. This is your fine setting, which is this is 0 to 1 millivolt, and this is a constant variable rheostat. Okay, let me just make sure that's all plugged in. Now we continue around here. So you've got two buttons here. You've got your test button and you've got your standard button. And there is a potentiometer here, a multi-turn pot here for the standard. Now, I'm going to be brutally honest here, I don't know what that's for. I really don't know what that would be for. I need the circuit diagram to actually see, because normally with the standard you don't need to change it. Standards, the interesting thing with standards, you cannot draw any current through them. They are a voltage device and they are voltage only. As soon as you start drawing current in them, it will slowly destroy the cell. So it's only a voltage device, but I'm not sure what that potentiometer does. Need to wait for the circuit diagram. Now, what I've got, so we've got 5 millivolts coming in. We've got it on the 1. We've got the settings set to the 1 over here. Settings to the 1. We've got 5. What I think is 5 millivolts coming through on here. Now, what I'll try and do here, I'll zoom in. That's as far as I can zoom in. So let's see. So you're looking at the galvanometer up here. Now, if I push the test button, I'm hoping, there we go. So what I've done, I've set the course to about 10 millivolts. Now, just let me check. Oh, sorry, I've got it on 10 millivolts. 10 millivolts at 100%. So I've set the course to 100 to 10 millivolts. If I push the test button and I just click, let me zoom out just a little bit here so you can see what I'm doing. Okay, so I push the test button. Now, if I click this one way, you'll notice that the galvanometer's gone off in one direction. If I go in the other direction, it goes off in the other direction. So, what I can determine here is it's around about 10 millivolts, because it starts to center, not quite centered, but it starts to center it. To center it, I then use the fine potentiometer, which is this one, and I'll go back over here so you can see the galvanometer. I'll push the test button and slowly turn this one, and it's coming back to zero, and that's pretty. I'm amazed they don't have a mirror on here for the parallax like they have on the Avo 8s. And we're at 0. So I can now read off, and let me go and see whether I can zoom in here any further. I can now read off. We're at 10 millivolts there on the course, and we're on, we are on, let me read off, so it's 10.648. I reckon that's an estimate. So 10.648 millivolts. So 10 is 0.01 of a volt. So 0.0. Let me write this down so you get a view. So we've got 0.0001. That's 10. That's 10 millivolts. Hang on, where are we? 10, 1, 6, 4, 8. 6, 4, and I estimate the 8. So that is telling me that the output of that power supply in this on that 100% is 10.648 millivolts. So when you think about it, this is a device from the 1950s. We didn't have super duper voltmeters and all sorts of things. And in fact, the voltmeter, let me just put the voltmeter on. The voltmeter minimum is 200 millivolts, and so let me measure what's coming in through here. I'm not going to get the sort of accuracy, so that's saying it's 10.0. It's just averaging what's there. Now there may be some load on that. Hang on. 10 point. No, it's exactly the same. So this device gives us the ability to become, for an even more accurate measurement, at 10.648 millivolts. So anyway, it's a bit of fun, certainly a bit of fun. Yep, we're right on the 10, and that's still centered in the 0. Now, hello Andy, hello, and hello to Richard from Tea Tree. So that's a bit of a blast from the past of a 1950s and all the way back to the early 1900s and into the 1890s, a Cambridge portable potentiometer. When I get it finally open, I will do another session on showing you what's inside, and hopefully I can. There's a few things. The rheostat on the millivolt potentiometer is a bit dodgy. There's something wrong with it, and the standard cell is not giving me the standard voltage out. So I need to do some work on that. But anyway, hold that thought. So that is a Cambridge portable potentiometer, and I'm not sure, Lionel, whether I will ever become the man in charge of the apparatus, but I'll try hard. But absolutely beautiful device. I got it through an auction house last Thursday. I didn't know whether I was going to get it or not, but I was lucky enough to be successful, and there you go. So sticking with our blast from the past theme, and people know that I collect Morse keys, I bought in a couple of very interesting Morse keys. This particular one, which is a thumping great key, which I'll take the hammer tone top off and show you up close. No, that's not right. Let's try that. That's a bit better. Zoom out here. This is what's been described to me as an ex-ship key. This is something that you would probably find on a ship. It is an AWA key, and in fact there is a nameplate on the front that is transmitting key type 3658D, serial number made in England by the MIMC Company, London. Now, surprise, surprise, that's the Marconi Company. It's interesting. It's a beautiful key. You can see the way it's made. They're actually ball races on both sides. It is a totally insulated key. So when this top is actually on, everything is insulated. And so if you're switching higher voltages through the actual key because of the transmitter, you are protected from those higher voltages by the cover. Beautiful key to operate. It is absolutely beautiful movement, which is what you'd expect with ball races. Manufactured expressly for the Amalgamated Wireless Australasia Limited, so for AWA in London. So beautiful key, ship key, ex-ship key, what you'd normally find on a ship. So that's the first one for tonight. Now this one looks pretty stock standard. This looks very similar to what we call in Australia a clipsal key. The clipsal key, it is on a cast iron base. That is a solid cast iron base, and it's got a very nice movement. It's not a ball race in here. It's just a normal bearing arrangement. You've got the adjustment for the spring and the adjustment for the gap, in the same way you've got on the other key. Now the interesting thing, and this is what really stood out for me when I saw this key and I bought this key. And let me zoom in here because this is fascinating. There was a stamp on the bottom, and that stamp had DCA, Department of Civil Aviation. So this is Australia. It's number one. It's an Australian key. Department of Civil Aviation. Number one, Western region. Now I've talked to a couple of the key collectors around this. They acknowledge that it was a aviation key, and they know where the Western region was, but they have never seen one of these keys. And on the front of it, there is a Y12-2. Let's see if that'll focus. Yeah, Y12/2 stenciled on the front of the key. Now, so I have actually not, I have very little information about this key, other than it's Department of Civil Aviation and it came from Western region. Got a bit of an idea about the age. We're probably talking 20s, 30s, 40s, that sort of era, probably more towards the 40s. But that's about all I've got for this particular key. Beautiful key, and it is absolutely, it is really heavy. That's all cast iron, so it's not going to wander around when you're as you're keying away. But absolutely fascinating, and it's a Department of Civil Aviation key, and very few people out there that I've spoken to in the know about Morse keys have ever seen a DCA key. So there you go. That wasn't a very good transition, was it? Let's go to there or there. How's that? Oh, that's a bit better. Still working out how to use the mixer. Now I'm going to give you a taster. A taster for next week. And the reason I'm giving you a taster is this particular device only arrived via FedEx literally this afternoon. So let's go to... Now this device comes from Cyprus, a little company called RADIACODE. It is a personal portable radiation detector. And let's do a little funny unboxing here. Comes with the obligatory scan the QR code, so tells you all the bits and pieces. Comes with the device. There is a USB-C cable here for charging it. It's got a little LiPo battery in it. Got a little display, got a radiation symbol on here, which is where the radiation detector is. It's a cesium radiation detector, all sealed and encapsulated. If we turn it on, there is a little display. There's a visual representation of the scintillation, and these things all tell you, these little lights tell you all different things. It's giving you the current reading in microsieverts, microsieverts per hour, and you can change that setting. Let me see whether I can get that a bit better. That's it. It's got the date and time. It's got the battery, and there is a range of, you get to a range of different functions through, yeah, here we go, through various menus that you can get to: device information, settings, spectrum, monitor, dose. So it is a radiation detector, it's a dosimeter, and it's a spectrometer. So it will actually tell you, or try and determine on the spectrum what sort of radiation you're talking about and what the source probably is. Now, to give you an idea of, that was the spectrum, hang on, I didn't mean to do that. Let's go back to monitor, that's it. Now, I have a 1942 compass, ex-Department of Defence compass, which I know has a radium dial. Now this radium dial, what I'll do is try to move these things past each other. This radium dial, you can see here, this is painted on radium, so on the little pointer you can see there are little off-coloured pointers, and there's a couple on here, the north, there's a couple on the pointer, and there is a line of it here. That is radium paint, so it glows in the dark. If I zoom out here a little bit and I bring the radiation monitor somewhere near it, it's actually telling me that I need to be a little bit careful because there are high levels of radiation around this particular radium dial. Now it's obviously set fairly low, but it just gives you an idea, and I need to clear the alarm. But it's I'll just give you, and of course it is, there's an app for that, and so what it's telling you is it has Bluetooth arrangement here. It's giving you the radiation levels. You can see the radiation level went up really high, and if I bring the compass back over here, you can see the level going up. So there is all of the app. You can, come on, let's go back. The dose, the level of dosage, which as long as that's on, it's recording that dosage rate, so I get a dose over a certain period of time. Then there is a spectrum display, which I'll go into next week, which enables you to determine where that particular radiation is coming from, etc. So anyway, it's absolutely going off. But anyway, it's a little radiation dose and spectrometer. Now let me work out here how to switch it off. There we go. Power off. Okay. And the other really nice feature is the display. When you do this, the display flips over, so that's another little nice thing that I'll show you next week. But anyway, I'll go into a bit more detail about the app and the radiation meter, and bring in some other sources of radiation, and see whether we can determine where they're coming from. So, very good point, Sean. Next week is not a DATV night, it is a presentation night, and it is on the Surf Lifesaving radio network in Tasmania. So no, not next week, week after that. Give me an extra week to work out how to drive this, which is probably good. So yes, thank you, Sean. Good reminder. So next week, Surf Lifesaving radio network of Tasmania. And then back to our normal DATV nights. Reminder that February the 18th is our AGM and special general meeting as well. Starts at 12 noon with a free barbecue, and then 1 p.m. for those meetings. And then on the March the 6th, so the March presentation night, we have Mars Butfield Addison, who is a PhD candidate with UTAS, giving us a talk on space junk and amateur radio. So that should be absolutely fascinating. And we've lined a few others up too. So we'll see what becomes of those. So anyway, that's our show for tonight. Thank you for putting up with the nuances of the presentation, gods. I hope it gave you a bit of historic insight. And we'll do it all again in a couple of weeks' time. So 73, thanks for watching, and we'll catch you next time. This has been VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Nights. Catch you next time.